previous video, we looked at where gas powered cycles are used, and we looked at some classifications of these power cycles in terms of gas and vapor, in terms of internal and external combustion. And we also looked at some important assumptions that are required for simplified analysis of these gas powered cycles. And those are called air standard assumptions or air standard cycles. And when we add to that assumption, these the 4 assumptions that constitute the air standard cycle, when we add the assumption that Cp and Cv values are constant, we get what are called the cold air standard assumptions, and the cycles that we analyze using these assumptions are called cold air standard cycles. So, we are going to use the cold air standard assumptions today to look at one particular external combustion gas power cycle, that is the Brayton cycle. So, this Brayton cycle is very important in 2 important applications. One of the applications is aviation. Most of the jet planes today that carry passengers and cargo are actually powered by Brayton cycle. And many of the gas turbines which are operational today that convert natural gas or diesel or naphtha or gasified coal to electric power are also gas turbine, and therefore, also Brayton cycle powered. In addition, Brayton cycles are also used in naval propulsion, especially for naval warfare ships and vessels that are used in the Navy. So, we will look at the Brayton cycle in some detail and try to understand what drives the efficiency of these Brayton cycles, and how can we change the operating parameters of the Brayton cycle to suit us and to benefit the particular application that we are talking about. So, what we are going to do today is Brayton cycle. The Brayton cycle consists really of 3 very simple components. Typically, air is drawn into a compressor, which compresses it to a high pressure, and as a result of compression, the temperature of the air also rises to some extent. And next, this compressed air is routed to a combustion chamber, where it mixes with fuel that is added separately, and there is a combustion process that releases a lot of energy, and so therefore, the temperature of this mixture of gases that come out of the combustion chamber is very high. Now, this combustion occurs at more or less constant pressure, and so we have a high temperature, high pressure mixture towards the end of the combustion chamber. So, the air going into the combustion chamber has high pressure, and the fuel combustion with the air increases its temperature further, and we have high temperature, high pressure gases coming out towards the exit of this combustion chamber. And then this hot, high temperature, high pressure gases are then expanded in a turbine to produce useful work. So, this is the simple component wise description of a Brayton cycle. However, there might be things that we can notice. That first thing that we notice is this is not really a cycle, in the sense that air is drawn into the compressor. This is fresh air from outside, and then it undergoes combustion. What we have here are actually the products of combustion, and these are expanded in the gas turbine, and what are exhausted out is actually the exhaust gas, which is depleted of oxygen, which is depleted of fuel, but is probably rich in carbon dioxide, water vapor, bit of carbon monoxide, bit of unburned fuel, maybe perhaps a bit of unreacted oxygen, and a whole lot of nitrogen, carbon dioxide, and so on. So, and these are exhausted out typically into the atmosphere, and so the cycle is actually not completed in reality. However, to understand this combustion process, to understand the cycle, it is beneficial for us to assume that this is air throughout, that is this is anyway air, but we ignore the fuel as we discussed in the air standard assumptions as well as the cold air standard assumptions. We ignore the fuel because the mass flow rate of the air is at least 15 times that of the fuel, and so we could safely ignore the presence of the fuel as long as we account for the energy released during combustion. We account for that through an assumption that has heat being added to the air from outside, and then we assume that this is also air, these combustion products are also air, and what is exhausted out is actually air instead of combustion gases. And so, therefore, once we cool this air, we can route it back into the intake of the compressor itself. So, in order to complete this cycle, we need an artificial imaginary heat exchanger that basically loses heat to the ambient and gets the exhaust gases of the turbine back to the state where they can get into the compressor. So, that is what we are going to do. So, this is model, and this is cold air standard. So, we have the compressor, and in this model this is an isentropic compressor. Which draws in air and exhausts it at a relatively high pressure and moderate temperatures, and in this combustion chamber heat is added from outside. So, this is Q dot in, and this then results in high temperature high pressure gases, which are then expanded in a turbine. This is again an isentropic turbine, and the exhaust from the turbine is cooled in a imaginary heat exchanger and then at the exit of this heat exchanger, the air is returned back to its original state. Let us call this state 1, let us call this state 2, and state 3 and state 4. And this heat rejection process is isobaric, and the heat addition process is also isobaric. So, to summarize, the process consists of an isentropic compression process followed by an isobaric heating process, heat addition process, followed by an isentropic expansion in a turbine, followed by an isobaric heat rejection process that returns it back to its original state. Notice that we assume that the compressor is isentropic, the turbine is isentropic as well. In reality, it is likely to be having a lot of internal irreversibilities. However, for this particular example, we are going to assume that this is isentropic, and we are also assuming that this is an isobaric heat addition process. In reality, this is air reacting with fuel to reach very high temperatures, and so we ignore the chemical reactions. We assume that certain amount of heat is added to the air, and such that there is no chemical change. It is just that air increases temperature as it goes from 2 to 3 because of the heat addition process, and the pressure at 2 and the pressure at 3 remain the same, that is the P 2 equals P 3. And then again we assume that the turbine is isentropic and it does work on a shaft and this is a compressor which requires work, and again we assume that there is a artificial hypothetical heat exchanger that basically rejects heat from the turbine exhaust gases, the air coming out of the turbine, and then restores it to state 1, and this heat rejection process is also isobaric, and that but this component is completely fictitious. It does not exist in reality, because in reality the gases are exhausted from the turbine and fresh air is drawn in. However, for analysis purposes, it is very reasonable to assume that there is a fictitious heat exchanger, especially when we are assuming that the working fluid is air throughout, and we are ignoring the fact that it mixes with fuel and undergoes chemical reactions. So, let us look at how this looks like on a TS diagram. Let us assume that these are the isobars. So, this is P equal to P 1 and this is P equal to P 2, and because this is an isobaric heat addition, we can reasonably assume that this is also equal to P 3. So, this is equal to P 3, and because this is also an isobaric heat rejection, I can assume that the pressure at 4 and 1 are the same. So, this is also equal to P 4 and so the compression process begins at, let us say, at state 1, and compressed, the gases are compressed or the air is compressed to state 2 in an isentropic compressor, such that the entropy does not change. So, this is S 1 equal to S 2, and then there is an isobaric heat addition to reach state 3, and then there is an isentropic expansion such that the entropy does not change again. So, S 3 equal to S 4, and this is an expansion in an isentropic turbine, and then there is this fictitious heat exchanger, which basically is the heat rejection step that restores the gas to its original state 1, and so this is an isobaric heat rejection process. So, that is how the Brayton cycle looks like on a TS diagram. Now, let us calculate or estimate what the efficiency of this Brayton cycle will be using the cold air standard assumptions. So, the efficiency of such a turbine is equal to the net work done, the rate of net work done divided by the rate of heat addition, and this can also be written as 1 minus q dot out or rejected divided by q dot in. And so, we need to estimate now the heat rejected. So, this is state 4 here. We need to estimate now the heat rejected in step 4 to 1 and the heat added 2 to 3. So, we can, using the same assumptions that we had used for the vapor power cycles, we can use 1 minus q dot out is m dot times H 4 minus H 1, and this is divided by m dot times T 3 sorry H 3 minus H 2, right, and this is assuming a steady flow such that the same m dot is used for the heat addition as well as the heat rejection steps. And so, I can write this as 1 minus H 4 minus H 1 by H 3 minus H 2. And we can also write for ideal gases undergoing constant pressure, we can write delta H as C p delta T, provided that C p is constant. So, recollect that C p is dou H dou T at constant pressure For ideal gas, we can write Cp as dH dt, and we can write delta H as integral Cp dt, and if Cp is constant, we can write this as Cp delta T. So, we can write this as 1 minus Cp times T 4 minus T 1 divided by Cp times T 3 minus T 2, and we can get rid of Cp and write 1 minus T 4 minus T 1 by T 3 minus T 2. So, what are the assumptions here? The assumption is that it is a steady flow and that the changes in kinetic and potential energies in the heat addition and the heat rejection steps are not significant, and so we can write this as m dot times H 4 minus H 1 divided by m dot times H 3 minus H 2, assuming a steady flow process. And then we can cancel m dot, and we also recognize that for an ideal gas, Cp can be written as dH dt, because H is only a function of temperature for an ideal gas, and delta H can be written as integral of Cp dt. However, assuming that cold air standard assumptions are valid, we can assume that Cp is constant and write this as Cp delta T. So, H 4 minus H 1 can be written as Cp times T 4 minus T 1, and similarly H 3 minus H 2 is written as Cp times T 3 minus T 2. So, we have 1 minus T 4 minus T 1 by T 3 minus T 2. So, we will continue on the other side. So, this can be written as 1 minus T 1 T 4 by T 1 minus 1 divided by T 2 T 3 over T 2 minus 1. However, we recognize that for isentropic process, T p to the 1 minus gamma by gamma is a constant. So, for instance, 1 to 2 is an isentropic compression. So, I can write T 1 P 1 1 minus gamma by gamma equals T 2 P 2 1 minus gamma gamma. So, in other words, I can write T 1 over T 2 as or T 2 over T 1 as P 1 over P 2 1 minus gamma. This can be written as P 2 over P 1 gamma minus 1 by gamma, and we recognize that P 2 equals P 3 and that P 1 equals P 4. So, we can substitute this T 2 over T 1 equals from here we can write this as P 3 over P 4 gamma minus 1 over gamma, and because 3 to 4 is also an isentropic process, we can write that this is equal to T 3 over T 4. So, we have this relation that T 2 over T 1 equals T 3 over T 4. Now, we take this and put it into this one here, and so we can write this as eta equals 1 minus T 1, and so therefore, we can write here T 4 over T 1 equals T 3 over T 2. So, T 3 over T 2 minus 1, this is T 2 T 3 over T 2 minus 1. So, we can take that term out and write it as 1 minus T 1 over T 2. Remember that this is not the same as the efficiency of a reversible Carnot cycle. It looks like that, but it is not, because there is no one temperature of heat addition. There is also no one temperature of heat rejection, because the temperature continuously rises when heat is added isobarically, and temperature continuously decreases when heat is removed or rejected in an isobaric manner. So, therefore, there is no one temperature of heat addition or heat rejection, and also this is only valid when the cold air standard assumptions are valid and not otherwise. And so, therefore, it is important to recognize that this is not the efficiency of a reversible Carnot cycle, rather this is the expression for a simplified Brayton cycle that follows an idealized cold air standard cycle, right. So, therefore, this is just 1 minus T 1 by T 2, and we can also write this as equal to 1 minus P 1 over P 2, and this is gamma minus 1 over gamma. Sorry, T 1 by T 2. So, T 1 by T 2 is P 1 by P 2, yes, or this is 1 by this is 1 minus 1 by R to the gamma minus 1 by gamma, where R is the pressure ratio. P 2 over P 1. So, the efficiency of a air standard cold air standard Brayton cycle depends on the ratio of pressures, that is the ratio of the pressures of the compressed air versus the atmospheric air. And so, typically air is compressed to a very high pressure in order to achieve higher efficiencies. However, as we will see, there are certain limitations to this pressure ratio, and we will look at that on the other side. So, we saw that for a cold air standard Brayton cycle, the efficiency was equal to 1 minus 1 by R to the gamma minus 1 by gamma. So, in other words, as the compression ratio increases, the efficiency increases as well, and the compression ratio is nothing but P 2 over P 1. So, it might appear that we should then compress the air to a very high pressure. However, we are again limited by material limitations, because when we compress to a very high pressure, the resultant temperature is also very high, and so typically this is a limiting temperature. So, this is the temperature of safe operation limits for the materials that make up the gas turbine, and so therefore, there is always a maximum limit for this temperature. So, although higher and higher pressure ratios will theoretically give higher efficiencies. It is not always possible to have extremely high pressure ratios, because then it would result in hitting this temperature limit very early, and so therefore, the efficiency then will actually come down. So, in reality what happens is that when we have very high pressure ratios, assume that instead of 2 we had gone to state 5, then the isobaric heat addition would take us to state 6, and then isentropic expansion would take us to state 7. So, the efficiency of this cycle 1, 5, 6, 7 would be low, right, because we are limited by this maximum temperature here. So, given a minimum and a maximum temperature, the efficiency actually undergoes a maxima when we try to increase the pressure ratio rather than increasing monotonically with the pressure ratio. So, this is an insight that we can get. So, higher pressure ratios are good. However, the pressure ratio has an optimum value beyond which the efficiencies start dropping for a given minimum and maximum temperatures that materials can withstand. So, with this we will end our discussion about the Brayton cycle, and also this ends the series of thermodynamics for the undergraduate course at IIT Gandhinagar. It was a very good experience making these videos, and we do hope that these videos helped you in better understanding the material that was presented to you in class, as well as the material available to you through textbooks and other online materials. And we will be happy to answer any questions that you might have in class, or you could also write to us using email. And so, thank you very much, and we hope to see you in another series of lectures on different topics at IIT Gandhinagar.